This is very important, and this part one is 100% will be included in the final exam. So please, at least you need to know how to uh, calculate based on the uh, the transformation. Okay, so last time we just stop here. That the whole idea is the original region of the integration is like this one. This is the I should say this is a new coordinate UV, but the original one is XY. But if the region G and region R can be mapped one by one to one to one from G to R through these two functions, S is equal to G of UV, Y is equal to H of UV, then we call R is the image of G, and we also G is the pre-image of R. So let me just directly go to the result. So if you want to integrate, okay, you can see R is here, the right hand side, right? If the original integration focuses on region R, and the function is f of x, y, then dx dy, can we just change the form from dx dy to du dv through this transformation? So you can see based on the formula here that we can just convert it into double integral. This time which is over g, not over r, and the function will be converted as f of g of uv common h of uv. So you can just image that here the result will be blah 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 x plus blah 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 y, right? But after the conversion here, the whole integral will become blah 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 u plus blah 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 v and du dv. But don't forget, we need to add Jacobian here, and Jacobian actually is a determinant like this one. So after we add this one in, then we can just totally convert the original integration into the new form of the integration. Why should we do that? Is we can to simplify the calculation. Even though at this moment you will see, okay, it seems that it becomes more complex than before, but through some example I show you, you can see that after the conversion, the calculation can be simplified. Okay, so I also show you some example last time that especially for the RC type coordinate is one of the special conversion. So that's what through the idea we can see why when we just integrate in the polar coordinate, we need to add a additional R here, right? Last time I also show you. In section 4, we just introduce this R by its original idea, but here we just based on the coordinate transformation. So our first example is this one, right? So original, this is the integration, like this one, and the integrand is this one. So after the conversion, you can see the conversion. After the conversion, I just directly go to the result to show you what simplified form we can get. You can see this one is much simpler than this one. Did you have a basic comparison, right? Finally, you just deal with this integration. But originally, you need to deal with this integration. So it looks this one much simplified than this one, right? But how can we do that? So in the beginning, you need to use these two constraints. I mean, these four constraints for parameters to construct the origin area of integration. So based on this, through these 4 parameters, you can get this one, right? Then since this problem just acts as to apply the transformation like this one. So the transformation here is you can just use xy. Each point xy can be mapped to one point in uv. So you can use this one. But of course, for this case, you can just convert it into s is equal to blah 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 uv and y is equal to blah 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 uv. So you can see, even though originally the question, the problem just give you the conversion by u is equal to blah blah blah, v is equal to blah blah, but you need to convert it into s is equal to blah 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 uv and y is equal to blah 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 uv. Okay, u and uv. So through this, this is the original area of integration. We need to convert it into g. So how can we do that? Because based on this, you can just figure out its original area of integration. So based on this, as I remember, I also encourage you just add the x in and y in based on which variable will be integrated first. So for example, this is dx. So we just put x here. Inner integration will need be taken care first, right? Then go for y. So after we add x here, y here, then we can get this figure, this area like this one. Then you please just remember to make a table. Make a table for original. If we just based on xy, the original boundary is this 4 9s, right? How can we just get these 4 9s? Because these 4 parameters. Then once we just establish that where, then try to get its corresponding UV equations for the boundary G. So right now, this is just focused on boundary of R, but we try to convert it into the boundary G for the same area. So how can we do that? Because right now we know x is equal to u plus v, y is equal to v. Then we just replace the variable in the original xy equations. Like this one, x is equal to y over 2. So when you just encounter x, put u plus v, because s is equal to u plus v. If you encounter y, please just put 2v in. Then you can see we just have a new equation. And through some calculation, finally we can just simplify as u is equal to 0. So similarly, you can do the same operation on the rest 3 boundaries. So for example, x is equal to y over 2 plus 1. So when you encounter x, please just use u plus v. When you encounter y, please use 2v. Then after you have this, after you simplify the equation, you can get this one. So finally, originally you have these 4 equations, but after the conversion, after the transformation, you can get the simplified 4 equations, 4 boundaries for the new area, for the new integration. So after that, you can draw the region just like this one. U is equal to 0, so u is equal to 0, we're here. U will equal to 1, so u is equal to 1 is here. Then v is equal to 0. V is equal to 0 and v is equal to 2. So finally, the original region of the integration is this one, and the converted region for the new integration will be here. And then you should try to establish the new integration. So the new integration will be here, okay? Because right now you already use u to replace 2x minus y over 2. So the original integration form is this one. Through the conversion, you will simplify it as u. But don't forget, you need to add in the Jacobian here, then du dv, then du dv. In Jacobian here, we'll just follow this determinant. Okay, and this is a Jacobian, the determinant. But when we just add it in, we need to add absolute value here. So, okay, since it's positive, so we can just simply use the 2 here. So this is a new form for the integration. And you can see the integrand is much simpler than this one. So through this conversion, your calculation for the integration will become simplified. And it will be easier for you to get the result based on the new form. Okay, so next time I also give you the second example is this one, right? So let's just also very quickly go through this one. You can see here is square root of s plus y, and the second term is y minus 2x squared. So this time, this problem didn't tell us the transformation, so you can just set up the transformation by yourself. For example, we dislike a complex form under the square root, right? So why not we just set u to be x plus y? And similarly, we dislike a complex form here because we need to calculate its square. So why not we just set it to v? So we just let u is equal to s plus y, v is equal to y minus 2x. So I believe for when we just all this part in the one variable equations, we also did the same thing. We just use a complex form by we just use a simple variable to replace a complex form. So here the only difference is in the past we just use one variable, u, but this time we have 2 variables, so we use 2. So once we just assign u is equal to s plus y, v is equal to y minus 2x, then through these 2 equations, we just converted. Finally, this is from SY angle, but this one is from, no, this one is, we just have u is equal to blah, 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 u, xy, v is equal to blah, 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 xy. Then we just convert it into s is equal to blah, blah, uv, and y is blah, 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 uv. Then we can use the original parameters to construct the original region. After we just construct the region, we can know it's a triangle. It's a triangle. So after we have the conversion, we try to convert these 3 boundaries into another 3 boundaries. So how can we do that? Also, just make a table like this one. So original, these 3 lines is s plus y is equal to 1, s is equal to 0, y is equal to 0. So through the conversion, then you can get the new boundaries for the new integration. So finally, you will face the region as this one, so that we try to simplify the original integration like this one. So you can use u and v to replace these 2 complex forms. Then don't forget you need to add in the Jacobian here. And this, if your integration order sequence is dv first, then we need to, as I always remind you that if dv first, remember to draw a line passing the region which is parallel to the v-axis. So if we just emit a ray toward the region, so the first, the enter point is here. So enter point is v is equal to negative 2v to u. Then leaving at v is equal to u. So this is the inner part. After you just control the inner part, where then try to collect all slice from u is equal to 0 to u is equal to 1. Then finally you can get the final result. Okay, so this basically two very I cannot say it's very simple. At least it will cost some time for you to find the final result. So I hope at least you need to fully understand these two examples. And then today I plan to give you another example, and then we just finalize this session. Okay, so let me just show you another example. Okay, so this example is just like that. Try to evaluate integral from 1 to 2, integral 1 over 1 y. The integrand is square root of y over x times e to the power of square root of sy dx dy. So you can see in the beginning this dx, right? The inner part is dx. So remember adding x in for these two parameters. Because in this form, we will go for dx first. That means we will integrate the integrand from the x direction first. So we can add x in. Then we will go, then later we will go for dy. So remember add y in. Okay, so this is the first step. So based on this, you can see here is a little bit complicated, right? And another one is this one. So why not? Let's just let v is equal to square root of y over x, and u is equal to square root of sy. So that means we try to simplify it as v, and we try to simplify this part as u, right? Originally, the form is complex, so we just use a single variable to replace it. So later on, you can see the integrand will become simplified. Okay, so let's just let this one, we just assign this one. Then after that, we can know that v squared is y over x, and u squared is equal to sy. So yes, that is not that hard, right? We just take the square at both sides for these two equations, so we can get these two equations. So we can continue to get u square. Okay, so let's just, if this is form 1, this is form 2, so let's just use 1 multiply by equation 2, so we can have v squared times u squared is equal to y over x times xy. So we can get v square u square is equal to y square, so that we can have y is equal to uv or vu. Okay? So why we can have this one? We just simply multiply these two equations. And follow a similar rule, we can just use 2 divided by 1. What will happen? 2 is u square over v square is equal to sy over y over x. Right? If we we just calculate 2 over 1, so we will have u square over v square. For the right hand side, we will have xy over y over x, so that we can cancel the common y. So we can get u square over v square is s square. So we can get s is equal to u over v. So you can see originally we have v is equal to blah blah blah, u is equal to blah 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 xy. Then we just convert it into s is equal to blah blah uv, y is equal to blah 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 uv. Right? So that we can just calculate its Jacobian. Its Jacobian uv is equal to partial x, partial u, partial y, partial u, then partial x, partial v, partial y, partial v. So that we can partial x s here is u over v. Then partial v, partial u, partial u, partial y is u v, u v. Okay. Is that correct? U v x. So when you just calculate this part, you must be very careful. U v. Okay, correct. So after that, when you calculate its partial derivative, it will be 1 over. So for this part, we can get is 1 over v. Then this part is u. This part is v. Right? Then for this part, it will be negative u over v square. Because when you just calculate this partial derivative, we should treat v as a variable, u is a constant. So that means you just differentiate 1 over v with respect to u. Then the next term here What's the last term? What's this one? U, yes. So that you can calculate its the final result is U over V minus U V squared times V. So we can just cancel 1. Then finally, we will have 2U over V. Right? U over V come from this part minus these two terms times together. So it will be, finally it will be 2U over V. So right now we already prepared the Jacobian ware. So, but don't forget, we need to have its form. So let me just show you the form, or the original form will come from here. Did you remember I told you? Original form will come from here, right? So that we can just have SY equations for the boundary of R. So for the beginning, we have 4 boundaries. One is S equal to 1. S is equal to 1 over Y. Then second one is S equal to Y. Then Y is equal to 1. Then Y is equal to 2. Right? Based on these 4 parameters, you can see the first one is S equal to 1 over Y. The second one is S equal to Y. So just this name there. Right? Then the second part is Y is equal to 1 to Y is equal to 2. So we have these 2 equations. They are just partial boundaries for region R. Then we try to get its corresponding. So just like here, we also need to make a table like this one. We need to get its corresponding UV equations for the new boundary, right? So here we try to get UV equations for the new boundary of G. So first one, when we encounter X, right? When you encounter X, S is here, S is here. So we will use U over V to replace X. Is equal to 1 over Y. Y here is UV. So we will have UV. Right? Similarly, for S is equal to Y. So when we encounter X, it will be U over V, then equal to UV. Then finally, Y is equal to 1, UV is equal to 1, and UV is equal to 2. So based on this, we can get the simplified. This is the simplified. And we can get U is equal to 1. Then the simplified one, we can get V is equal to 1. Then this one, we can get UV is equal to 1, or we can either u is equal to 1 over v, or v is equal to 1 over u. Both are fine, you know, because they are just try to express the same curve. Okay, so the original, these 4 lines, it will just lie here. The original one is in S1, right? So the first line is S is equal to 1 over 1. So the line will just like this one. This is S is equal to 1 over 1, right? This is the first one. The second one is S is equal to 1. So S is equal to 1 will be like this one. This line is S is equal to 1, right? Then the intersection is 1, right? Because you can easily to use these 2 equations to solve. The answer is 1, and here is also 1, right? Then the third one is y is equal to 1. So this is y is equal to 1. And then y is equal to 2. So we can see the region bounded by these 4 lines that will be here. Right? Based on the equation, based on this, we can get this one. Should I make it smaller so you can have a whole picture? Based on this 4 parameters, then you can construct the region of the integration, right? Then, since right now we have a new coordinate system, is u is equal to 1, u is equal to, so let me just draw the new coordinate in u and v. So one is u is equal to 1. This is u is equal to 1. Then this is v is equal to 1. Then u is equal to uv is 1. uv is 1 is here. Oh, sorry. This is uv is equal to 1. Then this one is uv is equal to 2. So finally, the new region is here. So the hand side is in S1, but through the conversion, through the transformation, you can get the new region for the new integrate. So the region will focus on this one for this part. So based on this, we can construct this integration, right? So based on this, we can try to integrate the inner part. Is why not we just choose this direction. If I draw this one, it's up to you, you know, it's up to you. You can also follow this direction first. But if I choose to follow this direction first, if I choose follow this direction, that will be dv first. Do you agree with that? Because I just follow the ray which is parallel to v axis. So if I just draw this like this one, then we will go for dv first, right? Then v we have from 1 to v is equal to 2 over u, right? If I follow this one. And then we will gradually collect all slices in terms of different u, so that we will go for du length. Then we can have u is from 1 to 2. As I told you, you can also try. If I go for this first, you will construct different integration form, but that doesn't matter. If you just follow your step, you can just carefully finish everything, then the result should be the same. Okay? Then we need to take care of the integrand, right? For the integrand part, originally the integration form here, you can see this is y over x, but I just assign it as v. So you can see here will be square root of v. Oh no, I just assign v, so we don't need to have square root of v. So we just assign it as v, right? Because we just assign the whole, item as v, and we are just assign the whole item as u. So then we can v times e to the power of u. E to the power of u. But don't forget that we need to add in the Jacobian. The Jacobian is this one. Jacobian is 2u over v. So this is a Jacobian, 2u over v. This is a Jacobian, 2u over v. Right? So let me just make it smaller so you can have a whole picture. Your always make it become very small, but you can just have the whole picture. Just look at here. You can see the original integrand is, here is u. This is square root of y over x is v. Square root of sy is u. So you can have these two terms. So it will be simplified as u times e to the power u. Then don't forget that we already prepared Jacobian here. That will be 2u over v. So this is the new integrand form. So compared to this one, it is simplified. But don't forget that you need to convert the area of integration into this new area of integration. Then we will just try to focus on this, how to calculate it. So after we get this one, all we need to do is about the calculation of integration. So here v can be cancelled, and 2 can be moved out of the integration. So we will have 2, 1 to 2, 1 to 1, 2 over u, then u du dv, then du. So for this inner part, it's easy, right? Because you just integrate it in terms of v. So for u, e to the power of u, they are all constant. So after that, we can have 2, 1 to 2, Then for this part, it will be u times e to the power of u v, then 2 over u and 1, then du. So we can have 2, then u times eu times 2 over u minus u times e to the power of u times 1, then du. So the integration form will become 2 times e to the power of u minus u eu, then du. So you can regard this as 2 minus u times eu du. So for this part, I will skip this part, but you can try to use integration by parts. Did you still remember integration by parts? You should assign here as u and this is d, u dv. So if you forgot, go back to chapter 8, we learned integration by parts to solve the equation. So finally, the result will be, through some calculation, you can get the result is 2e times e minus 2. So what I want to emphasize is still several steps. The first step, so about the calculation, I believe you can do it by yourself. But what I want to emphasize is, the first thing is try to simplify the expression. So we just use these two expressions to replace the complex form here. Then after that, this is the first step. Try to watch what term will be replaced by u, what term will be replaced by v. Then after that, this is our first step. Then after that, we will just confirm or transfer from u is equal to sy, v is equal to blah 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 sy, convert it into s is equal to blah 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 uv, and y is equal to blah 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 uv. So you can see for this part, originally it will be v is equal to blah 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 x, blah 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 y. This is u is equal to blah 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 x, blah blah y. But you need to convert it into s is equal to blah 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 u, blah 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 v, y is equal to blah 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 u, blah 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 v. As in the beginning, we just say this is g of u v, this is h of u v, right? So after that, this is the second step. You know the transformation and you know how to convert uv become xy. Then try to get the Jacobian. And then you can get this one. When you just calculate the Jacobian, this is the third step. Just remember the determinant. So sometimes the determinant will just confuse you because it will look a little bit complex. But then the first step is the original xy equations for the boundary. You need to use the transformation to convert it into uv. Okay, so according to these four equations, you can construct the original integration area, the area for integration. Then after you just convert it, you can get this new one. So this is the first step. Then finally, we just use the transformation and use the new boundary to construct the new integration form. Then you can get this one. the last step, I cannot say it's not important, but the next normally you need to use some integration tips to solve the calculation of integration. OK， 我很快把这几个步骤讲一次哦。我说过这一定会考，200%会考，这算不算泄题？对不对？哦，所以而且我已经讲了3个题目了哦。那这个算是里面是稍微比较复杂一点点的啦。哦，我再把这个重点再讲一次，就是当给你一个式子积分的时候啊，你记得要去找出它的，本来是如果你看上面的式子看起来很复杂，记得找出一些比较重要的一些比较复杂的形式呢，把它换掉。以这个例子来讲，它就是把这个 u 跟 v 做这样指定。当你指定了 u、v 之后，记得你要把它转回用 x、y 的角度来看。所以你刚刚是 v 等于呱呱呱，这个 u 等于呱呱，你要转过来变成 x 等于呱呱，y 等于呱呱。好，那有了这个指定之后，就好像我们开始在论述了，你会有 s 等于 g of u-v，y 等于 h of u-v 这样的一个形式，你就可以拿来算你的Jacobian。因为我们当做这个转换的时候呢，你中间会缺一个项叫做 Jacobian 的称，所以这个计算上我就 skip 过去，但是要注意这边会有4种组合嘛，对不对 ？s 对 u 偏为 y 对 u 偏为 s 对 u 偏为 v 对s 对 v 偏为 y 对 v 偏为，就这现在算的时候常常之前啊，因为这几年我们都没有考到这一段，之前同学在算这一段就会比较混淆，而且比较花时间，要么就算错，要么就是花比较长时间去算到，但这部分要小心一点。好，那这部分如果处理掉到了第3步骤的时候呢，就是你原来的积分的区域啊，这4条线来自于哪里呢？从你的原来的积分式子去取得，得到这4条线，然后呢，经由你刚列出来的这个转换式，看到 s 就换成 u 除以 v， 看到 y 就看成 uv， 所以用这个方式呢，把你的这个 s 跟 y 呢翻译成 uv， 所以你4条线全部把它翻译出来的时候，变成这4条线，变成这4条线。所以我们就画个图来做个比较，原来的积分区域如果用 SY 坐标系统来看的时候，它是这个积分区域，可是转换成这样之后，它的积分区变成这样子。那接下来最后一个步骤，应该是最后的倒数第2个步骤，就是我们把积分的积分式呢做一些改变变成简单的 v 跟简单的 u， 去取代你刚刚比较复杂的根号 x 除以根号 sy 还有根号y 除以 x， 对不对？那同时呢，你可以选择这积分区域出来，选择我要从 v 先积分，还记得吗？我说过，如果你要积分的时候，如果是往这个方向 v 先积分，就是记得画一条线平行于 v 轴，射向这个区域，看它从哪里进去哪里出来嘛，对。所以它的进入点呢，就是从 v 等于1开始进去，对不对？离开的点呢是在 v 等于2除以1。好，那这一段会算之后呢，我们接下来收集所有的不同的 u， 所以 u 会从1一直到2，就整个积分式子就变得比原来的式子简单许多。那中间你看到这一段我跳过去，不过课本有给你 hint， 这一段的计算呢，事实上是透过分布积分法，所以不要忘了，我们在第8，其实越到后面可以验收前面大家忘了多少的越多，对，这边就是用分布积分法，在第8章，不要以为到这边前面都忘光了。当然，其实积分越到后面还有什么旋转体、表面积啊、旋转体什么都可以弄进来，你知道吗？这都是合法的不是到后面就不能考前面的所以积分的技巧里面有用到 integration by part， 这是用 integration， 所以这个步骤算起来说实在很复杂。但期末考的时候啊，我们就我先把题目列一下 这几天 hope you can just have some idea about the triple integral in rectangular coordinates. Okay, the rectangular coordinates means the traditional Cartesian. Hello. Wait. Okay, so I will just briefly introduce this part to you. But before that, I just want to show you. Did you still remember when the double integral, the function is z is equal to f of y? So sy, so that means the region we are just focused on some region in the sy plane. So compared to triple integral, that means we will not just have two variables, not just s and y, but also z. So in this case, our region, original is a plane region, will become a space region. So just like this one. But for each point in the space region, we will map to a function value through w is equal to f of syz. So that's why we always like to use double integral to introduce the multiple integration to you, because double integral, it is easier for us to visualize it. 我们为什么常常在讲这个多重积分的时候，其实多重积分不限定于只有二重积分，有3重、4重、5重，但是我们为什么常常喜欢用2个变数的？因为它可以完全的具象，从它的定义域，从它显示出来的曲面，以至于到它算出来的体积，其实整个都可以画。可是到3重积分的时候，其实它已经只剩下哪里积分的区域可以具象而已，至于它已经没有所谓的这个乘以这个的值的比较从几何角度的物理意义了啦。不过到后面的什么线积分的时候，其实它其实还有它自己的意义，所以没关系，反正就是大家其实在双重积分的时候有这个概念的时候呢，其实不妨把它想象到多了一个变数这样的想法。Okay, so we also can use the Riemann sum to express the idea. So you can see we still follow the idea to have some partition in x direction, in y direction, as well as the z direction. So finally, in the past, maybe it's just a small rectangle here, but here it will become a small cube. Okay. So if we want, and then the integration will just, the form will just like this, triple integral, then the function, then dv, or normally we will dz, dy, then dx. So when you still follow the rule for the double integral, if dz, remember, emit a ray toward the region in parallel to z-axis. 所以这原理都一样的哈。如果说它现在是 dz， 一般都 dz 先了哈，那一定是怎么样？往这个积分的区域呢，从平行与这个 z 轴这个方向往这积分区域呢，去射出一条线，就看它从哪里 enter， 哪里 leave。OK， 所以我要讲的就这一块哈，等一下再讲。And we also can simply let f of syz is equal to be 1. If we just simplify it is 1, then we can just use this one to calculate its value of its region. This is the same as when we just set the integrand as 1 for double integral. Even though we are just trying to calculate the value, but the size is the same as the region, right? So we can also let the integral as 1, then we can simply get the value by calculating this integration. So how can we just calculate integration? So you can see this is a little bit complicated. You know, when I just this part to my student for my first time. I have a dream. Someday we can just wear the glasses. Then every student in the calculus class just wear the glasses. Then you can just see the 3D model. It's a pity so far I didn't implement it well. So someday maybe I have some student can help me to do that. But you know, right now we already have some AR VR glasses, so I think it will not be a daydream, right? Okay, so in the future, I believe otherwise you need to tolerate my bad drawing. You know, this is drawn by my hand, so it will not look so beautiful as you see in your textbook. But it's really made by myself, so even though it looks not so beautiful as the picture in your textbook. Okay, so the first step for us is still sketch the region. So the region will include, so normally the region will describe by z is equal to f2 of xy, z is equal to f1 of xy. Then after that, you can just have a bird view from z side, then see that will be project to be projected to the xy plane. So that will form the region R. So original is D, but when you just project these two surfaces onto the xy plane, you will see a region R here. So after you go back to it just come to a 2D region on xy, you can just follow double integral. Then if we just follow dy first, then remember that emit a ray parallel to y-axis. Then see which is the enter point, which is the leaving point. Then you can construct the integration for y part. Okay, so draw a line parallel to y-axis, and then you can find the y limits of the integration. Then finally, because it has already been reduced to double integral, so finally we try to collect all pieces, subpieces from the x angle. So finally you can have this one. So you can see it's almost the same. If you just hide z part, then actually you will come back to double integral. 所以这观念其实都一模一样，对不对？哦，只是差别在哪里？这会比较复杂一点点。这个 region 的描述呢，不再只有 x 跟 y 的范围而已。还记得吗？我们这两个变数的时候，会有一个 y 等于 g2x 跟 y 等于 g1x 的这样的区域。所以你如果不看 3D 或看 2D 的话，就是回到我们二维的这个积分区域，双重积分。但多了三重积分，多了第三个纬度的时候，它一定会告诉你两个曲面去包覆出来这个 3D 的 region， 就是它会有一个上曲面跟下曲面去包覆出来。那它当它从把它 project 到 xy 平面上的时候，它就变成这 R 区域。那大家想象不要去管其他，然后看到这个 R 区就剩下 x 跟 y， 所以一样的，如果有先对 x。先对 x 或先对 y 的问题的话，如果先对 y， 你就对 y 平行设一条线，看它从哪里平行。所以观念其实呢，当然它事实会更复杂的哈。So this is example. This is example. So you can see, find the volume of the region D enclosed by the surfaces. Z is equal to blah, blah, blah. This is the first surface. And the second surface is Z is equal to another blah, 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 S and Y. So these two surfaces will construct the region of the integration. So this is the upper region and this is lower region. They will construct the whole region in the space. Okay, So in the beginning is dz, right? Dz. So remember, we just emit the ray parallel to z axis and see which service will enter. So the first, the enter point will be z is equal to x squared plus 3y squared. And the leaving point is z is equal to a minus x squared minus y squared. So then you can just construct the first, the most inner part integration here, right? This is enter point, this is leaving point, and then try to use these two services to construct its project region in in the xy plane. So how can we do that? We can just use these two equations to solve. Then you can see these two equations, these two services, their intersection is this one. This is an ellipse. So we can just image that when we just project these two, the intersection of these two services, we can get it will be an ellipse. So for the ellipse, then you can continue to divide the ellipse into two parts. One is the upper part, one is lower part. So from the lower part as the enter point, and the upper part is the leaving point. So you can construct the y limits for this whole integration. And finally is to end for this ellipse from the x angle. Then you can get negative 2 to positive 2. So finally this one. And I believe we can just image that the calculation will take a lot of time to do that, because you need to solve the inner part first and gradually extend it to y part, and then finally to x part. So it's not that easy for you to finish the calculation within several minutes. So that's why we will not include this part into the final scope. Okay. So this is so we also can try to get the average value for a function in space over D. So it's also the same, right? You can see if we can calculate the whole integrals, the value of the integration divided by its whole volume of the region, then you can get the average value. 所以如果你要算它的平均值的话，其实跟二维的也是一样的，对不对？我先去算它的整个积分的值，去除以它的区域的体积大小，一除下来就是它的平均值。那是很快的给大家一个概念哈。14-15讲完了啊。放心啊，不会考，但是一样稍微知道啊。那我们接下来就讲14-7， 14-7我就觉得比较难一点哈。So, in section 7, we were talking about another two types of coordinate. One is cylindrical coordinates, and the other one is spherical coordinates. For the cylindrical coordinates, so did you still remember that in the previous section, each point in the space is s, y, z, right? S, y, and z. So if we just follow cylindrical coordinate, 柱状的坐标系统的话，它会怎么做呢？ It's simple, because in the past we can just simply convert sy into r theta system, right? We just keep z as the same, but for sy we just simply be replaced by r theta. That's all. That's all. So for each point syz, for each point syz, you can see z is still the same. But for xy part, you can use S is equal to R cosine theta, Y is equal to R sine theta, and also R squared is equal to S squared plus Y squared. So if you just focus on these three equations, I believe that is not hard for you to image that, because when we just learn polar coordinate system, we already know how to convert the point in the Cartesian coordinate system into polar coordinate system. So by using these three equations. So in the past, each point that will be described as R, theta, and Z. So so this part is just give you some quick idea that if I give you an equation, theta is equal to theta 0, actually it will replace as a plane containing the z-axis. So did you remember? Okay, let's just go back to the polar coordinate system. If we don't have z, each point will be expressed as r theta. So at that time, if I say theta is equal to theta 0, this will just represent a static line. Did you remember? When we talk about r is equal to some constant a, for the polar system, we will say that will be a circle. Did you remember that? 我们在极坐标系统是用二维的哈，二维的。我如果写作西塔等于45度角，它在描述一件什么事情？是一个斜的45度角的斜线，对不对？我们在讲这个 r 等于 a 的时候，在二维的再讲一下，就二维的这个极坐标系统是 r 等于 a 的时候，我们在讲这是一个什么？是一个圆，是一个圆，对不对？可是现在它是一个三维的坐标系统，它多了 z。如果我写西塔等于西塔0的时候 ，z 是 any 的话，代表什么？任意的高度伴随着西塔等于西塔 0， 它是一条线，所以任意的高度斜着某一条线上面，任意的高度，那不就是一个一个斜的平面吗？对不对？同样的，如果 r 等于 a， 原本在二维的时候，它应该是一个圆，可是因为你的 z 是任意值，所以它就长起来 ，z 的高度长起来。它就变成一个柱状体了。哦，用这个观念去想，那如果 z 等于 z0呢，它就一个平面嘛。哦，这边有点小小的复杂，不过没关系，你就尽量听了哈。Okay, so if we want to calculate the integration based on the cylindrical coordinate, so it will also like divided into small pieces, and each small piece will just like this one. Okay, then the integration will be by using the Riemann sum. Then you can get this one. This is the integrand, then dz. Then remember to add in r when we just calculate the double integral in the polar coordinate system. We always need to add additional r here. So for triple integral, the most inner integration will be f dz. Then adding additional r, then dr d theta. So if you just hide this part, actually you just go back to the double integral in the polar system. R dr d theta. OK， 所以如果你把最内部的那个把它去掉不看的时候，事实上基本上它又是回到二维的，你会加上一个 r， 在 dr d theta， 而且我们也只有 dr d theta 这个顺序了，对不对？所以如果你是走注重坐标系统的话 ，OK, so it's almost the same. The idea is almost the same. We also have an upper surface that will be described as z is equal to g2, G2 of r comma theta, right? So this is the upper service. We also have another service, we call it lower service. Z is equal to G1 of r theta. So finally, through these two services, we can construct the region for the integration. And then remember to emit, because you can see dz first. So you also will emit a ray toward the region in parallel to the z-axis. So you can see which is the enter point, and the enter point is in which service, then which is the leaving point, and the leaving point is located in which services. So this is the enter point, this is the leaving point. So similarly, if we just project these two, the intersection of these two services onto the xy plane, you will get this region on xy. And this xy will follow the star angle is alpha to beta. And then the region is enclosed by some upper curve and a low curve. But these two curves will be described as r theta. That means it's a polar equation. It will be a polar equation to describe the upper and lower curve. So again, I just give you another example that you should, the first thing for you need to try to draw the upper surface and the lower surface and see when you just want to integrate it in terms of z, then remember to emit a ray in parallel to z-axis toward this region. Then you can see which is the enter point, which is the leaving point, and then you can construct the most inner integration for the whole integration. So this is the inner part, and then it will be reduced to a polar curve to do the double integration. So you can see here that we will add r in the dr dc. So for the rest part, it will just follow the integration for the polar coordinate system. 所以这个呢，看起来呢，其实我们慢慢的再调整一下，就把本来的 xy 呢，就改成 r 西塔，所以呢，它一样的在积分的这个曲面这个区域里面呢，首先一定会有一个上面的曲面跟下面的曲面去包覆这整个积分区域，所以一开始最内层的那个积分呢，就会被由这积分区域会从某一个下面的积分区那个曲面一直延伸到上半部的积分区域，所以它一定会有一个进入点跟一个离开点。那怎么样去得到这个呢？跟我们以前学到原理一样，就是它既然是底 z 呢，就是沿着 z 轴去射向它，然后去找出它的进入点跟离开点。那它一定会是 z 等于 r 西塔到另外一个 z 等于 r 西塔。这个题目都不好做了哈，这个题目一下来，光画这个曲面的概念，可能要花掉很多的时间啊。但是我起码要有这个概念啊。那剩下的 r 西塔的积分就回到我们在做二维的极坐标系统的积分了哈。Okay, the last one is the spherical coordinates. So we just gradually extend s, y, z to r theta z. Then finally we just convert each point as rho, phi, and theta. It's a spherical coordinates. Rho, phi, and theta, how is just defined as this one. So rho is the distance from P to O. So if in the space we have point S, Y, Z, this is the traditional, this is the Cartesian coordinate system, S, Y, Z. If we just map to a point in the spherical coordinate, it will become rho phi theta. So how can we just get the rho, then phi, then theta? Rho will be the distance from O to P. O is the origin, right? This is the rho. It's easy, right? Phi will be the angle OP to OZ with the positive z-axis. So this is the positive z-axis. This is the OP. So we can get the angle between these two rays, right? 所以这个 phi 角是什么？取的是 O 到 P 这条射线跟 O 到正极方向的夹角。OK， 那第三个 theta is the angle from cylindrical coordinates, just like here. Did you remember we have R, theta, and Z? So theta here is the angle from cylindrical coordinates. So theta will be ranging from 0 to 2 pi. Okay, so if we want to convert the space point from the spherical coordinates to the Cartesian and the cylindrical coordinates, you need to follow these equations. So that's a lot, right? So R is equal to phi sine rho sine phi, and using S is equal to R cosine theta, Y is equal to R sine theta. Then you can continue to convert it into rho sine phi cosine theta. Y is equal to rho sine phi sine theta. So you can see the first step is from SY to R theta. But since we already know R is equal to rho sine phi and R is equal to rho sine phi, so we can replace R with rho sine phi, then continue times cosine theta and sine theta for x and y respectively. 好，所以这个 rho sine R 等于 rho sine phi 不会太难看，对不对？为什么？你注意看，这个 R 的大小，虽然画的不漂亮，但是起码还算看得出来了哈。你看，如果这个是 phi 角，这个 rho 是这个长度，所以当你要得到这个 R， 如果我可以得到这个暂时的 R， 在球状坐标系统里面不会有 R 的。柱状坐标系统有 R theta z， 对不对？在球状坐标系统里面没有 R，R 是一个暂时性的产物。那我们怎么样把这个 rho 跟这个 sin 本来是 R theta 呢，变成这个跟这个 rho 跟 theta 的关系呢？事实上就是这个，把这个夹角 phi 呢去乘以它的cosine 值，就可以得到这个 R 的这个sin 值，你就可以得到这个长度的。rho 去乘这个 sin 值，就可以得到这个长度。那就把 project 到 xy 平面上，就得到 xy 平面上面的 R theta 的 R。And then you can also use z is equal to rho cosine phi. So the height will be converted as rho times cosine phi. So that you can get the height. So that's why we just need to learn XYZ system first, then go to R theta Z system, then finally rho phi theta system. Okay, so you can see it will become a little bit complicated, but it still can be realized by these equations. So again, if we just simply say rho is rho phi, this is an equation in the space that will express that low is equal to low 0, then theta and phi can be any value. So finally, it will be represented as a sphere. So phi is equal to phi theta. It will be a cone. It will be a cone. And finally, if theta is equal to theta 0, that will be a hairpin. So I just give you a very quick concept about this coordinate system, because in I'm not sure in your physics class, I believe you also use this coordinate system, right? Did you? 你们在那个物理课的时候有用到这个稍微做这样？没关系，没用到也没关系。电磁学的时候用到了，所以我现在只是想说，让你们先尝个不算甜头啊，有个印象，避免这个上电磁学的时候，老师复习这段是完全没有概念的哈。其实，在上电磁学的时候，前面老师也会把这个数学再稍微带一下，但电磁学的时候一定会用到这个哦。所以你现在如果能够多花点时间先学一下，也不是什么坏事啊，不然碰到电磁学的时候。那个也是很痛苦的，对不对？哦，不过这个就是几次看下来，你就慢慢知道它是渐进式的，从原始的原始的卡式作业系统变到柱状作业到球面作业系统的时候，哦，它就有它的慢慢衍生的道理哈。哦，那这就很难画了哈，我也想不到我当年这么厉害，画的这课本画的比较漂亮，我画的。虽不漂亮，但是也应该蛮佩服的，因为这画的真的是要很3D 的感觉哈，所以还是看课本比较漂亮。不过你要知道，这个手工绘画是比较贵的，对不对？有没有？大家去吃饼干的时候，不是手工饼有没有比机器的饼干还贵的？有没有？有吧？对不对？啊，老师这个是用手工画的啊，所以比较值钱啊。啊，你们那教科书上面是电脑，是印刷出来的，所以这个比较值钱，对。下次再画也不会同样的这样的图，对不对？每年画的应该都不一样。好，所以一样的，它也是把它切成什么一小块一小块，这个已经不是什么，这算蛋糕吗？哈，但是它这边有糊的感觉哈，所以已经又有点变化了，这已经不知道这个要算什么图形了哈。所以不管它，其实到最后给大家看一下很恐怖的式子啊，就这个。So, in the cylindrical coordinate system, we just add R, but for the spherical system, we will add rho square, sin phi, d rho, d phi, d theta. We just follow this order, but we need to add this part. Okay, the additional part, like when we just deal with almost the same issue, we need to add additional R here. But for the spherical coordinate system, then we need to add these terms for the integral. So again, you must have a rho is equal to G2 of phi theta, and rho is equal to G1 phi theta. This is the bottom, this is the top. Then you just emit a ray from the 0, toward the region. Then you can see we will pass the first surface, then leaving the M surface, and then just project it to SY. Then you can continue to fix the limits for phi part. Then finally is the theta part, right? And then this is an example for the integration, for triple integration in the spherical coordinate system. So this is the upper surface. It's an ice cream cone. 啊，那冰淇淋那cone有没有？上面有一层，有一个这个曲面哈。 那他要去算这个这个有点小复杂了不过这个另外一个重点是什么？如果你把指定这个函数的值是等于1的话呢，你算出来事实上就在算这个体积啊，还记得吗？只要被积分式指定为1，事实上都是在算它的区域的体积或区域的面积，这概念是一样的，都可以延伸过来的那为什么？因为如果这式子再有更复杂的式子，你这算可能算不完，对。当你这边只有1的话，这边光 rho square sin phi 的计算就要够你算的所以大概是这样所以这大概是14之7。所以14之5跟14之7呢，其实我们不会考试的时候不会考，但是是希望大家在